So I'm John Hatcliff from Kansas State University, and this is joint work with a number of people, Adventium Labs, SEI, Collins Aerospace, and this is actually feeding into a number of different projects that we have going on, but I'll try to focus on the connection to CASE. So as Jen kind of gave an overview in her talk, the main objectives of CASE are to be able to somehow capture requirements for cyber resiliency in some sort of analyzable way, capture your architecture in an analyzable way, and then be able to automatically detect or discern if your architecture is satisfying those cyber resiliency requirements. If it's not, then CASE provides several different interactive tool sets that allow you to sort of rework your architecture model so that you meet those requirements. And one of the fundamental aspects of the CASE approach is the use of microkernel technology. And the idea there is that if you have a microkernel in place, you can use that to strongly partition components, make sure they're not interfering with each other in unanticipated ways. And you can also carefully control how they're interacting or communicating with each other. The nice thing is, if you need to do any of these transformations, it's very easy just to reconfigure the microkernel partitioning so that you can enable these different transformations and switch the way that components are talking to each other and so forth. So it's my opinion that this sort of microkernel approach is also very, very relevant for the whole DevOps story, where you need to be able to flexibly migrate your system, evolve your system, bring in new components rapidly, and so forth. So that's something to keep in mind. So the different types of transformations on CASE, Jen walked through some of those. One other that I'll mention here is a common situation on CASE is we have some legacy code. We need to bring it into the system, but it's untrusted. And so one of the things that we do is we drop that down into a virtual machine, and then that goes into one of the partitions in the microkernel. Then the others that Jen mentioned included putting in a monitor to see if the system was in a bad state, doing different types of attestation services where you see if the data that's coming to you is trusted and so forth, and then doing various types of filtering. So question, and Jen had this at the bottom of one of her slides, if you have this great architectural and analysis approach, how do you make sure that your deployed system conforms to the architecture? Right? And in her slides, there was a couple of bottom lines related to the whole system build framework. So that's what we're working on in collaboration with Adventium Labs and Collins Aerospace and Data 61 on the DARPA CASE project. So in a much broader context, the approach that we're sort of taking in our research group has sort of three abstract tiers. We think of things in this way. We have the AADL level where we're doing various types of analysis, including for CASE, various types of information flow analysis, checking of functional integration constraints like Jen mentioned. What we do is we take that AADL model and the analysis information, and we're able to automatically generate a simulation environment for that using Scala, which is a widely used language in enterprise. And in particular, we're using a subset of Scala that we designed called Slang that's designed for safety critical systems. So it throws out a bunch of stuff that would normally make it difficult to compile down to embedded platforms or to verify. But because we restrict ourselves to this subset, we are able to bring in a lot of automated verification tools at this level while still leveraging all the sort of the enterprise tooling for model-based testing and so forth and so on. So finally, after that Slang level, we go down to various types of embedded platforms. For CASE, we're focusing on SEL4, but there's a variety of others that we're working on in other projects. Again, what's happening here is we're not only sort of preparing to bring the application code down, but we're also generating code for all of the AADL sort of runtime infrastructure related to communication and threading and so on. So let me just say briefly that we're tackling some other domains besides this avionics domain. We had some DHS funding with Adventium where we developed a reference architecture called isosceles for medical devices, and we used this sort of approach to build an infusion pump that ran on that reference architecture, and we're connecting to several other domains as well. But let me kind of lay out the basics of how this approach works, and then in the demo we can jump into several different aspects if you're interested in that. So one of the things that's been emphasized throughout the day is that AADL isn't just boxes and lines, right? There's some notion of semantics associated with it. So what does that mean? Well, actually, it's like AADL provides this sort of semantic palette or collection of computational patterns that you would often see in real-time embedded systems. So there's a collection of patterns for threading, whether your threads are time triggered, event triggered. You can mix and match these within the same system. There's different sorts of patterns related to communication, whether you're doing pub-sub, for example, or shared memory communication, or several different types of others. And the idea is that in addition to sort of configuring the topology of the system, the developer is also choosing from these palettes to configure, in essence, a computational model or the underlying semantics of the system. So when the developer is picking out these different properties and attaching them to the model as annotations, what they really do is sort of defining an underlying semantics for how the threading is going to work and then how the communication is going to work. And so you can also start to introduce platform elements, like Etienne mentioned in his talk, where you're attaching additional information that says, oh, I may be going down to DDS, for example, or CAN with my communication primitives. So the idea is that, again, given this type of semantic information, what AADL does in its standard that's very nice is it also says, well, if you're going to interact with these underlying semantics, there's a collection of APIs that you should work with. And the code generation framework can implement the code however it wants, because you're going to be working with those APIs and you're going to be isolated from the distinctions between platforms for this various code generation. So the way that our tool, HAMR, right, stands for High Assurance Modeling and Rapid Engineering, the way that it works is it leverages this notion of semantics in the sense that when the system build process works, what it's going to do is do code generation for the computational patterns that were chosen in AADL. So for the threading, it's going to generate sort of wrapper code, or you can call it bridge code for the threading that was going to hook up to the underlying RTOS scheduling mechanism. You may be then also generating your communication infrastructure that may tie into, for example, for SEL4 with its interpartition communication, or you may be able to target some other middleware framework like DDS or so forth. You may be generating code for that. And then, of course, you're going to be generating some platform configuration information, right? But remember this important concept of being able to generate APIs according to the AADL standard, which it calls runtime services, generating these APIs that then the application developer can come in, program to realize the application code. And it's these APIs, again, that isolate the application code to a large extent from a lot of these platform distinctions. So on case, what that allows us to do is say, oh, okay, we want to deploy parts of the system to SEL4. We can do that. And so in that case, we're generating threading that's related to SEL4, its communication primitives associated with interpartition communication, right? And we have application code, for example, in C that works with that. But then if we want to do some transformations, say, oh, that really should have been inside a VM, or we want to move something from a VM out into a bare metal SEL4 partition, then we just reconfigure this code generation. And right now, I think I have some words related to Linux here. So we're using the Unix System 5 interprocess communication here. Just a flip of the switch and regenerates that infrastructure, but now for a different platform. So that's kind of the main idea, but I mentioned that there were sort of 3 tiers to our approach. And so now I'm going to tell you a little bit more about what's happening behind the scenes. The idea is that in addition to sort of this AADL layer, we're factoring things through the Slang framework. Now, if you don't like Scala or you don't want to touch Scala, that's fine. You can have it run, sort of produce stuff directly in C, right? But if you're interested in working at this layer, you can program your components in Slang, you can verify them using our framework, and then do the autocode generation here. What this gives you is, in essence, a pivot point in your code generation architecture. So we've actually programmed the infrastructure that we're seeing here that provides the semantics of AADL in Slang, and that allows us to sort of assure this once and for all, sort of the executable behavior of the AADL infrastructure, and that makes it very easy for us to plug in additional backends for different platforms. So for example, right now, we're supporting the SEL4 microkernel, but it would be very easy to adapt this, for example, to support the link secure partitioning architecture, other things like that. So that's kind of the overall story about how things work in this context. So just to emphasize what's really happening behind the scenes here is that this intermediate layer is really sort of providing a reference implementation. We're not claiming it's the reference implementation, but it's really a reference implementation for our framework and our semantics. And what that allows us to do is to really have essentially an abstract machine for analyzable real-time computation, and then get all the benefits of working in sort of a JVM-based framework where you can hook up to other sorts of enterprise tools for that. One of the things that I'll highlight in just a few seconds when I'm talking about some of the other things is once you're in this sort of framework, this enables you to do a lot of interesting simulation, fault injection stuff without having to actually go down to the board. Of course, you eventually want to do that and test at that level too, but we can talk about some of the other things you can do even at this Slang level. So in the discussions that follow, I can describe, if you're interested, about some of the restrictions on Slang that allow you to have very expressive programming language, but still be able to target embedded systems and be able to do different types of verification in the different memory models that are being used there. We can explain the different types of C backends and OS platforms that we're targeting. So these are the things that are right now being targeted on CASE, for example. One of the things that I'll mention is if you're familiar with the CompCert project, so that was one of the first projects that developed a verified C compiler that was sort of sponsored by Airbus to some extent. And so the C code that we generate is actually compatible with the CompCert C compiler. So you can see that eventually we're moving to and working toward a verified translation stack that will go all the way from, you know, executable code up to C and then up to AADL by building on that. So some of the things that we can talk about in the demo is as part of Army SBIR with Adventium, we developed a framework for simulating BA or blessed state machines that are part of the AADL standard. You can use the simulation infrastructure that's provided here in Slang to execute, simulate, visualize. You can see there's a history scrolling window. You can go back and forward in history and so forth. But then you can leverage this tool chain to actually compile that down to C to get a deployable system if you want to implement some of your components in BA or bless. We can take a look at some of the Slang. This is a simple implementation where you're seeing the Slang code here, and this is the calls to those APIs that I talked about that the AADL standard sort of mandates or designs, how we're leveraging those to make sure that we're sort of independent from the platform-specific code. One of the things that we can look at is in this framework, since you're working at the Slang level, it's very easy to use Java's mechanisms for reflection and other things to tap in and actually have a sort of a godlike observer of what's happening in the system. So you get in the framework the ability to sort of have an infrastructure here that can subscribe to different types of events so that as the system is running, you can do different types of analysis, collection, analytics, and that can feed into different types of visualizations where you have event streams. We use the ACA event stream library, if you're familiar with that, to do various types of event processing and so forth, visualizations for that. So this is just some of the output that sort of comes for free. Any system that you build, you automatically have the ability to sort of look at all the things that are being done on data ports, event ports, and you can define your own little projections that automatically show those up there. And then you can visualize those in various ways. You can just press a button and you get the message sequence chart, for example, of how all the events are being communicated in the system. So in the reverse direction, you can also do various types of fault injection. So again, using this sort of Scala JVM-based layer, you can very easily inject faults into the communication pathways and to the component state to do various types of model-based testing and so forth there. One final thing that I'll mention that we're doing on the CASE project is information flow visualization. And so what's happening here is that you can point these information flow tools at the AADL model, and we'll build these browsable information flow graphs that you can query in various ways. Just pressing a button here and saying, oh, I'd like to know where this particular event's information flows in the system, and it will automatically sort of through all the different subsystems and so forth trace out where that's going. So a variety of different visualizations and queryings are available with that. So to sum up, what we're trying to do is provide a flexible simulation and code generation environment for AADL, capable of supporting multiple languages and platforms. And so we're continuing to look at expanding this in different ways. A key aspect of what we're doing is designing all this for verification. So not only verification of the compilation translation, but verification of the application code. I've explained a little bit about how this connects to the CASE program. And in the discussions today, again, this is important to realize that we're connecting with several different groups. So Adventium Labs and Brian Larson's sort of demo of Bless would be most relevant to this. Thank you.